to all of you. At the first instance, I express my sincere thanks to the organizers for providing me the opportunity to share some of our research findings. And I also express my thanks to the chairman for introducing me. The topic of my today's presentation is development of electrochemical biosensors based on functional nanomaterials and enzyme immobilization. I would like to present my lecture with the following outline. In the beginning, I will briefly introduce the basic principles of electrochemical biosensors with special reference to the components, fabrication, functioning, and also the performance characteristics with reference to the electrochemical biosensors. And then I will be introducing some of the functional nanomaterials and their utility to improve the performance characteristics of the electrochemical biosensors. And then I will be elaborately describing the fabrication of some of the electrochemical biosensors. And I will be focusing my talk towards the methodologies like layer by layer, electrospinning, self-assembly method for the fabrication of some of the electrochemical sensors with the immobilization of GOX, SOD, 6C, COX, and HRP enzymes. Some of them are redox proteins. And in that process, we have fabricated many electrochemical biosensors for the analytes like glucose, superoxide, anion, cholesterol, nitrate, and nitrate ions, hydrogen peroxide, and so on. Generally, the sensors will comprise of three main components, namely sensing matrix, otherwise sensing layer, the transducer, and reduction system. In a typical sensor, the sensing material can be placed on the suitable physical transducing systems, and the physicochemical property changes in the sensing matrix can be transducted in the form of a signal, and mostly the physicochemical properties will be first converted into the form of energy, and it may be a radiant energy or electrical energy or mechanical energy or thermal energy. And depending upon the energy, say for example electrical energy, the physicochemical property changes such as the conductivity changes, potential changes, or current changes can be measured in the form of a signal. Okay. In the case of biosensor, the biosensor converts a biological response into a quantifiable, this is more important, quantifiable and processable signal. So in the previous speaker well explained the principle of the biosensor. I will be pushing certain aspects related to the electrochemical biosensors. So in the electrochemical biosensors, the bioreceptor may be a nucleic acid or an enzyme or cell can be placed in the sensing matrix, and this can be utilized for analyzing a variety of analytes. What is the speciality of the biosensor is the specificity which is being conferred from this kind of bioreceptors. The other biomimetic compounds also can be used for introducing the high sensitivity. So the physicochemical changes or biological changes in this part can be transcribed in the form of a signal, and the signal can be measured. Depending upon the type of the bioreceptors used in the sensing layer, maybe an enzyme, protein, or antibody, the biosensor can be classified with enzyme biosensor or immunobiosensor and so on. And the biosensor can also be classified depending upon the type of transduction. Maybe an electrochemical sensor, which we will be seeing elaborately after this talk. And the signal may be potentiometric changes, potential changes, or current changes, or voltammetric changes. What we will be seeing is mostly on the current changes. Electrochemical biosensors have gone through three generations. In the first generation biosensor, the electron transfer from the enzyme may be assisted in the presence of a physiological substances, maybe mostly oxygen will be chosen as a physiological substance. In the second generation biosensor, the mediator, which may be an organic compound or organic compound, may be utilized to transfer the electron from the enzyme to the electrode. In the third generation, the recent generation biosensor, the electron should be transferred directly from the enzyme to the electrode. Many characteristics are required for a commercial or practical biosensor. Some of them are mandatory and some of them are optional. And the mandatory ones are indicated in the red letter: sensitivity, detection limit, reliability, accuracy, and those things. But it's very difficult to get all these parameters in a practical or commercial biosensor. This slide listed out some of the important characteristics of the biosensors, and some of them are shown with highlights, yellow highlights, and these are all mandatory. What is important is these performance characteristics are to be reduced from the subsystems in the sensor. These are all the possible subsystems in the sensor, and one of the greatest challenges for the biosensor scientists is to reduce all these performance characteristics from these subsystems. Okay, so maybe nanomaterials with its intriguing properties can be utilized to achieve many of these properties in the performance characteristics in a combined way in most of the subsystems. From our research group, we try to exploit the functional property of many nanomaterials to achieve these performance characteristics in a combined way. Nanomaterials or graphite materials with the size ranging 100 nanometers. What is important are they possess intriguing properties like high surface volume ratio, catalytic property, plasma resonances, and so on. And these properties can be effectively utilized to improve the performance characteristic of the biosensors. Okay. What is more important is it is possible to manipulate the size, shape, architecture, composition, hybridization, microstructure of these nanomaterials, and we can tune the property that can be utilized to improve the performance characteristics of the biosensors. Nanomaterials can be grouped in as organic and inorganic biomaterials, and in recent period, the combinations of inorganic and bio and organic inorganic hybrid materials are also being utilized. So the nanomaterials can be classified based on the shapes also as 1 dimension, 2 dimension, 3 dimension. And this is a typical case of nanoparticles. In a typical case of nanoparticles, you can find a large variety of materials, maybe metal or semiconductor or some ceramics or polymers. So in one class of material, maybe nanoparticles, you can go into the variety of different kinds of materials. Therefore, a galaxy of materials available for tuning the property and to improve the performance characteristics of the biosensors. In a typical case of metal nanostructures, you can have various shapes like cubes and bars, right? So these are all the intricate nano shapes, and this is the case with gold. So, summarizing this information, I can say the nanomaterials can be prepared with different sizes, shapes, and compositions, and their properties can be properly utilized for improving the biosensor characteristics. So, these are the important information about the utility of nanomaterials in biosensor applications. So, I told you some of the beneficial properties which can be used. And besides that, that can be effectively used for enzyme immobilization because of the large surface to volume, large surface area, along with the functionalization possible with the nanomaterials. And what is more important, by just tuning the property of nanomaterial, it's possible to execute that electron transfer from the enzyme to the electrode system. And in that process, we can improve sensitivity, selectivity, and signal to noise ratio in a combined way. individual nanomaterials such as carbon nanotubes, nanodiamond, metal nanoparticles, conducting polymer nanostructures, nanofibers possess intervening properties which are beneficial to the improvement of biosensor characteristics. But from our research group, we exploited the synergistic properties of the combinations of many of the substances, and we tried to improve the performance characteristics of the biosensor in a combined way, with the selectivity and sensitivity. And I showed you some of the performance characteristics. All these things can be improved in a combined way. So in the next few slides, I will briefly mention about the importance of individual materials. Say, for example, carbon nanotube possesses very interesting properties like thermal properties, mechanical properties. Besides that, what is more important for the application of sensors are the high surface area, good electron transduction, and electrocatalytic properties. And this slide shows, irrespective of the type of analyte, maybe organic analyte or inorganic analyte or biochemical analyte, the catalytic current on the surface of the electrode, if it is modified with carbon nanotube, is very large compared to the other carbon materials. This can be effectively exploited for increasing the sensitivity of the biosensor. And when you think about the metal nanoparticles, gold nanostructures possess very intriguing properties like biocompatibility, catalytic property, and conductivity, and tunable properties. And because of that, many of the enzymes and biomolecules can be anchored onto the gold nanosurface. What is more important, the bioactivity of the anchored biomolecules can be retained when it is placed on the gold nanoparticle. Besides that, it can have good catalytic properties that can be exploited for transferring the electron from the enzyme in the case of enzyme biosensors. Nanodiamonds very interesting aspect for the biosensor application is the biocompatibility, and besides that, it has a very good operating potential. Using that, we can go for the oxidation of even compounds with higher oxidation potentials. Polymer nanofibers can be produced by a simple process known as electrospinning, and this can be used for mass manufacturing of nanofibers with nano diameters. What is more important, you can see the pores, internal pores in the nanofiber itself. This can be effectively utilized for immobilizing the enzyme. Okay. So these are all the features, the important features that are beneficial for the biosensor characteristics. Small diameter, large surface area, porous nature, and other things. So I will be explaining our research findings on the third generation direct electron transfer based glucose biosensors. Before going into that, I will briefly mention about the need for glucose biosensor. Okay. Diabetes mellitus is a metabolic disorder, and which causes changes in the insulin, and ultimately it causes changes in the glucose concentration level in the blood and the human blood. And this is a normal blood value, and when it is above or below, it is a normal blood value. When it is above or below this value, it can cause health disorder, especially heart problems and other things. And one of the statistics says glucose is the most frequently analyzed analyte. And possibly one of the reasons is due to the large number of diabetics available in the world population. Okay, so stringent personal control of blood glucose level becomes an important problem. Okay. So if you again look at the statistics, glucose biosensor account nearly 85% of the whole market, biosensor market. Okay. So several group of scientists are working on developing glucose biosensor. So several methods are available for monitoring the glucose, out of which electrochemical methods receives good attention. sensors, biosensors have gone through 3 generations. In the same way, glucose biosensor also have gone through 3 generations. In the first generation enzyme glucose biosensor, molecular oxygen is being utilized for transporting the electron from the GOX or the product from the glucose oxidation. But the problem associated with this kind of first generation glucometer is the oxygen dependency. Okay, so because of that, the values, the glucose values are not stable and not reliable. So in the second generation glucose sensor, which are being utilized in most of the commercially available glucometers, they utilize the mediator, mainly inorganic compounds being used for transferring the electron from the enzyme to the electrode. But here again, the problem is that mediator must be insoluble, otherwise it gives problem. Because Prof. Chung was explaining health care. If it becomes soluble, then it will give health problem in future, integration of wireless networks and the glucose biosensor. So it should be non-toxic also, because in recent period people are going for implantable biosensors. Okay, so there is a great need for the third generation glucose biosensor, eliminating the mediator and developing reagent-less glucose biosensor. So we try to use enzyme immobilization and try to make the wiring of the enzyme to the electrode with the help of the nanomaterials. So this is the one research what we have published and in bioelectronics, and here we have utilized hollow spherical conducting polymer nanostructure for the immobilization of GOX. So we prepared this hollow spherical polydiphenylamine nanostructures by using soft template assisted cell assembly approach. So actually, we prepared this kind of hollow spherical polydiphenylamine within the gallery of the MMT clay area. So we have a mixture of the monomer diphenylamine and naphthenic sulfonic acid was allowed to self-assemble within the gallery, and after that it was allowed to polymerize. Once the polymer is formed, then it was extracted, and this because beta-naphthenic sulfonic acid was used as a soft template, and it can be removed out, and you can get a beautiful hollow spherical nanostructure. This is the picture of the hollow spherical conducting polymer nanostructure, and the inner diameter is like this, 40 to 90 nanometers, and the outer diameter is 60 to 90 nanometers. Okay. So these the outer shell can be utilized for immobilizing the glucose oxidase. Okay. This was tested by using quartz crystal microbalance measurement, and sudden change in the frequency corresponds to the loading of the GOX, and we calculated how much loading was possible and tried to calculate the specific activity of the enzyme available in this shell layer, and then we checked whether the immobilized enzyme retained its bioactivity by checking with other chemical testing, dialysis test. We tried and we compared the activity by chemical method and activity actually present by way of loading the GOX. The close values clearly says that the immobilized GOX retains its bioactivity. That is more important. Only then it's possible to execute direct electron transfer. Okay. This is the direct electron transfer possibility was tested by means of electrochemical measurement. These are all the cyclic voltammogram of the polydiphenylamine nanostructure in the absence of GOX and in the presence of GOX. So in the presence of GOX, you can find clearly the redox peaks that corresponds to that GOX. Okay, so this is the redox transition corresponding to the prosthetic group in GOX. Okay, so actually we calculated the redox potential compared with the natural GOX, and the value is very near to the natural. So the the GOX immobilized in these nanostructures using its bioactivity, and we checked the direct electron transfer rate constant, and this is also very high compared to many of the matrices reported in literature. So we try to utilize the rotating ring disc electrode method for monitoring the electroactivity or electrocatalytic activity of the nanostructure loaded with the GOX electrode. Okay. So by increasing the concentration of hydrogen peroxide, we can find a clear increase in the current value, especially after this potential 0.4 or something like that. This corresponds to the oxidation of hydrogen peroxide. Okay. So we also check the current value with various rotation speeds. With the increasing rotation speed, the current also increases. Using that, we try to calculate the rate constant for this reaction, and it is found to be much higher compared to many of the matrices reported in the literature. This is the hydrodynamic voltammogram recorded at the electrode, and this is the electrode without actually the nanostructural material, and this is the response of the poly-diphenylamine nanostructure form. So it clearly shows the nanostructure forms provides high electrocatalytic for the oxidation. So we also tested the conditions of changing GOX and changing temperature and changing pH, and it's very interesting to note that the current value is maximum pH is very near to physiological pH. Okay. We also tested the ambrometric response of the electrode, and by just injecting glucose concentration, sudden change in the current can be seen, and it reaches a steady value within 5 seconds. This response is very fast, and it gives a steady increasing current values with increasing concentration of increases. And we made a calculation plot and tried to find the linear range for the current response, and this is very high, 1 to 20 millivolt. This is ideally suitable for the blood glucose monitoring for diabetic patients. And the sensitivity also is very high, and the detection limit is very low. Okay. What is more important, probably Professor Chung explained the future biosensors integrated in the human body, and when it is integrated in the human body, you need to have the sensor stable in flowing stream of glucose. Okay, so we check the stability of the electrode in the flowing stream of the glucose. This is the flow injection angiogram of the sensor electrode, and this value is very near. Current value is very nearer to each other. That shows the reproducibility of the same concentration of glucose was injected. And when we increase the concentration of glucose, the current value increases. So it shows high reproducibility and high stability, and shows linear variations in the concentration. Okay, so this electrode is ideally suited for analyzing the glucose in the flowing stream. So we also tested the possibility of interference with other interference substances like acetaminophenol, uric acid, ascorbic acid, and we tested like that. We just injected a mixture of glucose and acetaminophenol and checked with the current value, and in the absence of that, we again checked the current value. The current value becomes nearer to each other. It means that acetaminophenol did not contribute to any current. Likewise, we checked all these things. What is more important is we checked the practical viability of our electrode using renal blood sample analysis, and we checked with the values obtained with the help of existing glucometer. Okay, so we just try to make a straight line fit between the value calculated using the value determined from the real glucometer available in the market, and values determined by our own sensor and approach. So the closeness of the fitted values clearly says that this kind of material is ideally suited for the commercial glucometers. And the reproducibility also checked and stability also checked. So we compared, I told you our aim is to make combinational property improvements, not the simple property improvements. And we could achieve many of the combinational properties. I input the response time. Response time also is 5 seconds is comparatively very good for a practical sensor. So we also utilized another kind of functional nanomaterial. There we have utilized a new technique, namely layer by layer. So in the layer by layer, we included many nanomaterials, maybe CNT, gold nanoparticles, CP, all in one layer. Okay, so that we can improve many of the properties of the performance characteristics of the biosensor in a synergistic way. Okay, so one of the main problems in the biosensor is the leaching of the enzyme from the sensing layer. So we try to avoid this leaching by making the compact film with a layer by layer. Okay. So this can be achieved when the enzyme is entrapped in between two stable matrices. So we try to utilize this principle and try to make a very compact LBM. Okay, these are all the advantages of using LBL method. I don't think it will be necessary here. So okay. So this is a conventional method of making LBL film. Here, alternative layers of polyelectrolytes can be deposited. Maybe polycation and polyanion can be successfully or alternatively arranged in the form of LBL layer. And the process is very simple. Okay, dip in polycation, wash. Dip in polyanion, wash. Something like that. Okay. So this is the old technique. But in recent period, it's possible to include many of the nanostructural material in this LBL construction. Okay, we try to combine these two and make a compact film for the glucose biosensor. Okay, so possibly this is a very interesting thing. Okay, it's a sandwich. This sandwich becomes very attractive for the commercial purpose as well as for the diet purpose. When the components placed in between the two layers are very attractive. So some of the components which are beneficial to the health value can be included. Some of the components can be included for improving the taste. And besides that, we have to compromise with the cost and everything. Okay. So this is a very good example of how we can make a compact LBL film with many components which are beneficial to individual aspects. Okay, so these kind of aspects we try to utilize. Here I explained the polymer can be placed in one part and the metal nanoparticle can be placed in another. So this kind of LBL film can be constructed with multi nanomaterials. Okay, this is the nucleus of our idea for the construction of glucose biosensor. So we try to utilize this technique. We try to include many components. I told you carbon nanotube and conducting polymer and metal particles. All these things in one layer. And then we try to use the next layer as the glucose oxidase. Okay. So in a simple preparation, the carbon nanotube was grafted with polyaniline, and then utilizing the thiol group present in the thiol functionalized polyaniline, gold nanoparticles were electrodeposited, and the charge, the nitrogen was converted into positively charged species, and then the GOX is loaded on that using the electrostatic. Okay, so this is the one layer, and this is one layer, and we can make multiple layers. Okay, right. So the compactness of the compactness was checked by following the optical absorbance in these two regions. There is a gradual increase in the absorbance value corresponding to the polymer, a gradual increase in the absorbance value corresponding to the plasma resonance of the gold. So we also tested the linearity of the increasing the absorbance in terms of the number of layers. So when the number of layers increases, the amount of gold nanoparticle can increase, the amount of polymer can increase. Okay. So the compactness of the film was tested by leaching experiment. Okay. So the leaching experiment shows the stable incorporation of the enzyme without any leaching. Okay. So we also tested the impedance of the film with the increasing number of layers. The increasing number of layers, you can find the increase in the resistance. The glucose oxidase, if it is included in the film, it will increase the resistance. This also shows, the increase in resistance also shows GOF can be continuously included in the film. Okay? So this is a very interesting test. If layer by layer film is not constructed, then what would be the electron transfer capability of GOFs? So this is the impedance response for the layer by layer technique, and this is the layer by layer. So the current this gives the resistance in the interface. The resistance is very low. It means the electron transfer is facilitated when we make the particular. Okay. So we try to use these kind of layer by layer technique for establishing glucose sensor. And this is when the number of layers increases, you can find the response current will steeply increases. So just by manipulating the number of layers, it is possible to increase the sensitivity of the electrode. Okay. So this LBL film also is free from interferences. Okay. This is another kind of biosensor which we fabricated for superoxide anion. Okay. The superoxide anion is a reduction product of the molecular oxygen, and it is mainly useful for the signal transduction and other purposes in a positive way. But when it is present in large excess, it can cause cell damage and, as well as aging problem. So the reduction of superoxide anion becomes one of the important tasks for the bioscientist. So the problem with the reduction is the high reactivity of the superoxide anion and the short life and rather very low concentration. So all these three combined things makes the construction of the superoxide anion biosensors very difficult one. So we try to utilize the close penning method for creating the core shell type of polymethyl polyamine, core shell type polyamine. Is a electrospun composite nanofibrous structure, and after that we included gold nanoparticle over that, and then we tried to incorporate the SOD in this. So this is the electrospun fiber. Electrospun fiber in the absence of the added components, and this is the electrospun fiber in the presence of the added component. You can see the surface roughness, and that corresponds to the inclusion of the polymer layer as well as the erosion particle. Okay. So we could find direct electron transfer. May it take 5 minutes?
No, 4 minutes. Yes.
Okay. Yes. So we can get some direct electron transfer and from this, and we try to find the superoxide anion concentration by modulating SOD, and we could get the minority and so on. Okay. So likewise, we developed the main sensor, nitrate sensor, so these are all using nanodiamond as a monitoring material, and we tried to establish direct electron transfer from the cytochrome C, okay, and exploiting that direct electron transfer, we fabricated the biosensor, okay. Let me go to the final aspect. Maybe I will synchronize with Prof. Chan in the biosensor development. We also developed a good cholesterol sensor, which is a functional nanomaterial. Okay, I will summarize this in 1 minute. So, in the future aspect of the biosensor trend, we have to integrate the biosensor with the wireless sensor. So, as a wireless sensor network, and it must be implanted in one body and transmitting the power of wireless signal. And some of the biosensors integrated with the wireless networks are also available in the market. But the requirement becomes more stringent in biosensor applications. We need to think about biocompatibility, bioharmony, miniaturization, non-conformity. All these characteristics must be included in the biosensor, and so that this can be going for the next generation biosensor.
Thank you, Professor.